And we're going to start with a problem. So last time we talked about this beautiful notion of if we have the right kind of function we're integrating. So here, what do I mean by the right kind of function? Well, if you were to think of this here is a function, and I'll call this, for lack of a better word, for right now I'll call this m. And here, again, this is another function n. So what we're integrating here along this curve is something of the form m dx plus n dy. Now this kind of integral can represent many things depending on context. The way we sort of introduced it and motivated it was, oh, it's sort of like force. So I have this force, I'm trying to move along a curve, and I'm trying to find the total. Now it might be the case that we just have to grin and bear it and do it the long way. But there are some situations where it's like, that does not seem appealing. Now you'll see in this problem we have the following. We have this curve. It's a sawtooth curve. And it goes up and down. There's a total of 19 segments. Starts in the corner at 0, 0, ends at 1, 1. So I'll put a little arrow here so we know which way we're going. Now we probably would not want to do this integral by doing 19 individual line segments and finding out what happened. So here's the great thing is, if we're integrating the right kind of function, life is good. Now what do I mean by that? Well, I mean by conservative. So that what's in front of the dx is a derivative of some function, the potential function with respect to x, and what's in front of the dy is derivative of some function with respect to y. Then it's very easy to find these integrals. Now in this particular problem, we don't actually have the whole function. We're trying to figure out what the function is. Because we're told what the value of the integral is, and we're asked to find our value for b. So now we think to ourselves, all right, if we ever see a terrible curve, we should say, let's hope that it's conservative. So the process is we say, all right, this first thing, that better be what happens when we take the derivative with respect to x. So let's integrate this with respect to x and see what we get. What's the integral of negative pi sine of pi x with respect to x? Cosine of pi x. What's the integral of 4 times e to the power 1 minus x arctangent y? The integral of that with respect to x? The 4 arctangent y is a constant. So you just need to integrate the e to the power 1 minus x. What's that integral become? Yeah, it becomes a negative e to the 1 minus x. So we get minus 4 e to the 1 minus x arctangent of y. So that would be what we hope, if there's a potential function, the pieces that involve x have to look like this. Now we come to this part. We say, okay, f sub y, integrate with respect to y. B is a number to be determined, but it's a number. What's the integral of by with respect to y? A half times by squared. What's the integral of minus 4 e to the power 1 minus x over 1 plus y squared with respect to y? Yeah. All right, minus 4 e to the 1 minus x arctangent of y. Now, in order for this to work, there has to be some sort of compatibility. And the compatibility says that, oh, things which involve two variables have to match. Well, in this case, the pieces that involve two variables do match. Which means that we do have something which is a conservative function we're working with. In other words, it's a potential function. And our potential function is the following. The cosine of pi x minus 4 e to the 1 minus x arctangent of y plus 1/2 by squared. We don't need to have this twice because the reason it shows up twice is we have an x variable and a y variable involved. So in particular, we get that the integral along this curve, and I'll compress my notation here, m dx plus n dy, that's equal to this potential function evaluated. We take the end point and subtract the start point. So the function at the end, subtract the function at the start. So that would be the function at 1, 1, subtract the function at 0, 0. So suppose we put in 1 comma 1. Well, what do we get? Cosine of pi is negative 1. All right. Minus 4 e to the 0. Well, e to the 0 is 1. Arctangent of 1? Pi over 4. And then 1/2 b times 1 squared, which is 1/2 b. Then we're going to subtract. Let's plug in now 0, 0. Cosine 0 is 1. Minus 4 times e to the 1 times arctangent of 0. Arctangent of 0 is 0, so that goes away. 1/2 times b times 0 squared is 0. So what we end up with here is we have minus 1, then there's another minus 1, so that makes minus 2. Then we have minus 4 times pi fourths makes minus pi plus 1/2 times b. So that's what the integral will turn out to be. But we know the problem says, here's what the answer should be. The answer should be 5 minus pi, coming from up here. So we say, all right, let's simplify. We can cancel off the minus pi's. Minus 2 plus 1/2 b equals 5. Add 2 to both sides. 1/2 b equals 7. Multiply both sides by 2, and we come to the conclusion that this will work if we choose b to be 14. And so there's our answer, 14. All right, so there you go. Good, good. Well, that's just one beautiful idea. And in essence, what do we have here is we have this nice idea that's like the fundamental theorem of calculus. It says, you know, I really don't care so much what happens in between. I just need to know what's happening at the endpoints for a related function. So we're going to talk about another idea, which sort of also you can think of as a generalization of the fundamental theorem of calculus. But let's start with a really simple thing. So a little bit of notation. We're going to talk about integrals which are closed curves. So in other words, I start and I stop at the same point. And the way we denote this integral is we put a ring around the integral sign. So you'll see there's a little circle here. Sometimes when we're writing it down, we'll say integral, and we'll put a little loop around it. So what this corresponds to, when you see this notation, that means the following. It means that there's a curve that looks like this. In other words, it starts and stops at the same point. Now, one of the things that's true from what we talked about already about conservative functions is if I have one of these integrals where I start and stop at the same point, and I find the integral on that curve of gradient of f dot dr has to be 0. And the reason it has to be 0 is you take the function at the end minus the function at the start. But it's the same function. And so it's going to cancel out. And therefore you get 0. Now, that's beautiful. But there's a question, well, what happens if we're not a conservative function? Can we say anything? And the answer is yes. Yes, we can. This is called Green's theorem. And what is Green's theorem about? Well, before we state the theorem, let's talk about the setup. So what we have is we have a closed curve C. Now, if I have a closed curve C, I have a region that is contained by C. So if you like, a region which is bounded by C. And we have some notation. Now, you might notice that we've seen notation like this before. There's a symbol here that we use for partial derivatives. We also use it for another purpose, which is to indicate boundary. So if you see something where it looks like partial r, no. This in this case means boundary of r. So I have a region and I have a curve. But because we're talking about these integrals, orientation matters, so we need to somehow talk about the orientation of the curve. So the question is, which way do we travel on the curve? Because if I have this region, and if I have this curve, I could go in two directions. One might say counterclockwise or clockwise. And so how do you remember it? Well, the way I like to remember it is that you orient it so it's on your left-hand side. So you have to imagine that you come here into the plane, and you're standing on the plane, and you're walking on this plane. And you want to walk along the curve in such a way that the curve is on your left-hand side. Now, how do you remember this? Well, you just remember there's a song. To the left, when you walk the curve, keep the region to your left. Right? Very catchy. You're going to remember that now. You're going to be like, this is going to bother me for my ride home today. For 6 hours, I'm going to be thinking, to the left, when you walk the curve, keep the region to your left. All right. So, but that's the thing, to the left. Really what's happening here is it's an orientation coming into play. And orientation matters. Now you might say, how much does it matter? The answer is by a sign. And so if you're off with your orientation, you lose a sign. And then you'd lose a point. But we want all the points. So we're going to keep our orientation correct. Okay, now we've just talked about our setup. So our setup is, I have this region, and there's a curve that bounds it. Here's the theorem. If I integrate on the boundary m dx plus n dy, and there's no restriction on what m and n comes from, m dx plus n dy, this is the integral over our region, partial n partial x minus partial m partial y dA. So it's kind of a beautiful idea. It says, I can choose one of two things. I can either integrate on the boundary some function, or I can integrate over the interior something that looks like a derivative. Because if you think about it, this really is like somehow a derivative of some sort of m and n. And so it does feel very fundamental theorem of calculus. It says, fundamental theorem of calculus says, I have the interior of this curve, or I can look at the boundary of the curve. And the boundary of a curve, if I think about back in Calc 1, where I have an interval, the boundary are the two endpoints, a and b. So it says, I can either integrate over the whole from a to b, or I can just look at this function at b and this function at a. So we're saying the same idea. It says, look, I can integrate over the whole inside of something, or I can just integrate on the edge of something which is somehow an antiderivative of sorts. All right. Now, what do we have? Well, I'm going to give you a sketch of a proof of a special case, just to show you what's happening here. And you're going to see, we're going to pull out the fundamental theorem of calculus and say, aha, this really is just fundamental theorem of calculus applied in a nice setting. So suppose my region consists of two curves. I have a lower curve, C2, and an upper curve, C1. And there are curves which are nice in the sense that I can parameterize them as functions. So, for example, C2, I'm going from left to right. I'll write that as x, f of x, where x goes from a to b. And the curve C1, well, that goes from right to left. So I'm going to have it be negative C1. So negative C1, remember, when you talk about negatives, that just says go backwards. So negative C1 would go, again, from left to right, whereas C1 should go from right to left. And I'm thinking this as x, g of x goes from a to b. So in particular, what I have here is I really have this set into the plane. Here's a, here's b, and then I have this lower curve y equals f of x, and this upper curve y equals g of x. All right. So we can say that the integral along the boundary of m dx, well, I can always take any curve and break it up into pieces. So I'll do, okay, it's the integral of the top curve plus the integral of the bottom curve. All right, no problem. Now how do we integrate these? Well, we can use the parameterization. So if I'm integrating along the top, so C1, I'll use the parameterization x comma g of x. So everywhere where I see an x, I put x. Everywhere I see y, I put a g of x. And then I'm going from A to B. Now, why is there a negative? Well, because of the orientation got reversed. So that's where the negative comes from. Similar idea for the bottom curve. So A to B, m x f of x. Now, what do? Well, we can really write this and then the following way. This is the integral from A to B of m of x comma y evaluated from y equals f of x to y equals g of x. Remember this notation. This notation says you plug in the top function, subtract, plug in the bottom function. So if you plug in the top function, you get mx g of x, which is right there. If you plug in the bottom, you get mx f of x, which is right there. So it's sort of a way to compress the notation. And now you're thinking, well, wait a second, I've seen that notation before. That's the kind of notation I get after I do an integration and then I do an evaluation. Well, what would I integrate? Well, I want to integrate something where I have this y is what I'm going to evaluate. So I'll integrate the derivative with respect to y. And where do I integrate from? Well, between these two bounds, from f of x to g of x. So it's the integral from a to b, integral from f of x to g of x of partial m partial y. So this part right here, this is where we're using the fundamental theorem of calculus. And now we say, aha, that is precisely partial m partial y. So again, I'm just emphasizing this is a special case, namely if you covered up, I said there was no n, and you had a very special region. But once you combine enough special cases together, really this idea is what does everything. You just have to be very patient with your cases. So that's the idea. All right, so let's try this. Let's see what we can do. So, let C be the oriented curve which goes from 0, 0 to 2, 2 to 0, 2, and then it goes back to 0, 0. So let's draw what this curve looks like. So we're going from 0, 0 out to 2, 2. So we're going this way. Then we're going to 0, comma 2, which is here. Then we're going to go back to 0, 0, which is there. So this is our curve C. And we want to find the integral along this curve of the following. 3x squared y dx plus x plus arctangent of y squared dy. Now this does not look like a fun integral to do. Now if we were to do it using our techniques that we've talked about before today, we'd have to do 3 integrals. 1 for each line segment. So we'd have to do an integral for this part going down, this diagonal part, this horizontal part. For each one we'd have to do a parameterization. And then we'd have to actually integrate some of these functions. Some of these functions do not look very fun to integrate. Arctangent of y squared does not look very appealing. So we don't want to do that. Instead, we're going to do Green's theorem. All right, so what's Green's theorem say? Well, notice that this curve is a closed curve. In other words, it starts and stops at the same point. So there's this space here. So here's a space. That's our region. And we can say that, all right, here's our region. We'll call it R. So what happens is that by Green's theorem, we can say that this integral on the curve is an integral over our region. Of what? Well, let's pull the theorem back up. So here we have to be careful because we've got to make sure we get it right. So if I'm integrating m dx plus n dy, so whatever is in front of the dx, that's our m. Whatever's in front of the dy, that's our n. And we want to take the derivative of n with respect to x, subtract derivative of m with respect to y. All right, so that's our goal. That's what we have to integrate, dA. Now in our case, what happens? Well, what happens when we take the derivative of x plus arc tangent of y squared with respect to x? What do we get? 1. This part, which made us nervous, is gone. Nice. Okay, what happens when we take the derivative of 3x squared y with respect to y? 3x squared. And we're subtracting that. All right. So now we're down to a single integral, which is much better, because that's one integral. And we say, okay, now we just have to integrate this thing over the region. Well, let's see if we can figure this out. Well, that's 1 minus 3x squared. And, well, let's do dx dy. Where does y go from? 0 to 2. And where does x go from? 0 out to 0 to y. Because this is the curve x equals y. So, we integrate this. Well, this is integral 0 to 2. We integrate with respect to x. We're going to get x minus x cubed, evaluated from 0 to y. So this becomes integral 0 to 2 of y minus y cubed, dy. So that's 1/2 y squared minus 1/4 y to the 4th, evaluated 0 to 2. And we plug in 2. 1/2 times 2 squared is 2. Minus 1/4 times 2 to the 4th, that's 1/4 times 16, which is 4, which gets us to -2. That wasn't so bad. So once you have the tool, then the tool makes things easier. So when do you use this tool? The answer is you use it whenever you have a bounded region. So if you have a closed curve, say, okay, let's pull out our tool, because it makes things, in many cases, a lot simpler. Now, oftentimes what we'll do is we'll do the following. It says, we'll take our line integral, and then we'll find an integral, convert it to an integral over a region. But you can also go the other direction. So there's this really cool thing that used to, well, I mean, it still exists. It's not like they burned them all and destroyed them. But there's something that, there was this tool called the planimeter. It's a real word. And what is it? Well, it was a little device. It was a physical device. So you'd have it on your desk, well, depending upon what your profession is. And from it, there's this little tiny arm that would extend. There was a little thing there. And now, what would happen is you'd want to know, well, how much area is there in a certain region? So the way it would work is you take the device, you'd set it to 0, and you drop it down at a point, and then you'd move that tip around this part here until you got back to where you started. And as you moved it around, there'd be a little tiny mechanical counter changing values, sometimes going up, sometimes going down. And at the end, when you got back to where you started, the number would give you the area. So somehow, by tracing out what was happening on the boundary, it was figuring out what the area was. So what it was actually doing, it was doing an integral. So as you're moving the little tip, the stylus around, it was doing a computation. It was saying, okay, I'm moving on this curve. I'm going to figure out what's my current x value. How is my y changing? I can figure out what is x dy. And therefore, I can compute this line integral. Now, why is that useful? Well, so if you do now Green's theorem, So this x dy, this corresponds to what? Well, because this is our dy, that's our n part. So you have n sub x and m sub y. And you're probably like, well, wait, Steve, there was no m. Well, there was. It was 0. So that's why m sub y is 0. And so this line integral becomes the integral of 1. And if you integrate 1 over a two-dimensional region, what you get is the area. Because what's happening is you're breaking up your two-dimensional region into little tiny pieces. You're saying, what's the contribution from each piece? And the contribution is just how much area is in each piece. So when you add it all back up, you get the total area. All right, well, that shows you. Calculus has applications. All right, real-world applications. So we can do this to find areas of regions. So let's do the following. Find the area of the region bounded by the curve c equals a cosine t, comma b sine t, where t goes between 0 and 2 pi. Does anybody recognize what this curve is? What? It's a lot like a circle. If a and b were both 1, it'd be a circle. But because a and b could be something else, it turns out this is an ellipse, where in the x direction you go out by a, and in the y direction you go out by b. So what we're going to do is we're going to find how much area there is in this ellipse, and we're going to do it using a line integral. Okay, so according to the rule, so here's our curve C. We just need to integrate along our curve C x dy. So that will give us the area of our region. Now we do our translation. So if I want to integrate along our curve, we're going to use our time parameterizations, 0 up to 2 pi. So 0 to 2 pi. What does x become? A cosine t. So a cosine t. What is going to be dy? Well, it's going to be the derivative of y, which is b cosine t. And then dt. So this is our x dy. All right, so that's ab, integral 0 to 2 pi of cosine squared t dt. Now, how do we integrate cosine squared t? Power reduction. So this will be ab, integral 0 to 2 pi. Cosine squared is 1/2 plus 1/2 cosine 2t. Well, so we're getting close. AB, integral of 1/2. A half times t. All right. Integral of 1/2 cosine 2t. Well, there'll definitely be a sine 2t, but what's in front? 1/4. Because there's already half there, and there'll be another divided by 2 because of the inside. All right. Now that's going to be evaluated from 0 to 2 pi. So let's plug in 2 pi. So we're going to get 1/2 times 2 pi, which is pi. So we already have the AB, so we have AB pi. Sine of 4 pi? 0. Now we plug in 0. 1/2 times 0? 0. Sine of 0? 0. And therefore our answer is AB times pi. And that's it. Now, that's actually not so hard to prove. There's simpler methods to prove it. But this shows that, aha, it works. And it's kind of beautiful. It says somehow it doesn't necessarily, it's not the most obvious thing. I'm doing a one-dimensional type integral, but I'm finding an answer to a two-dimensional type problem. So that's all right. Math is good. Okay. Now, you might be thinking, okay, this is good, but can we somehow bring something else into it? Well, so let's get a little bit more holy. So what happens if we don't have a region which is one big piece? Maybe it's something which has holes inside of it. Can we still use it? And the answer is yes, it still works. But here's the thing. You have to remember the orientation. And that's why I like to phrase my orientation in to the left. Sometimes you'll see it saying, oh, go counterclockwise. But that's a little bit misleading. You want to make sure there's a consistency going on. So for instance, when I'm standing out here, if this is me and I want to go along this curve, the way to move along the curve so that the region stays to the left is to move in a somewhat counterclockwise direction. On the other hand, if I'm in the middle and I want to walk along this curve so I keep the region to the left, I would move in a clockwise direction. So you want to make sure you keep your orientation consistent. So to the left. And we're going to go up into a higher dimensional setting later on, so you want to make sure you're like, okay, how do I make sure I get my orientation correct? So just remember, to the left, to the left. Okay. Now how does this work? How do we justify it? There's a couple of ways you can think about it. Here's one way to think about it, and I like it this way, which is to say, well, let's actually cut it up. And the way we cut it up is we reach into our pocket and we pull out a pair of scissors. And we come in and we just do a and a. So we made a little cut. Now, what have we done? Well, what we've done is we've essentially said, now there's not any holes left. Because what's going to happen is we're going to move along our region, so we'll just follow the curve. And we move along, and when we reach the cut, we'll move down, and we'll keep traversing to the left, and then we'll move back up, and we'll keep going along. So now it's just one continuous curve. But you might say, wait, hold on, there's something wrong. We went down this part twice. Isn't that bad? Well, hold on, did we go down it twice? One way, we went down in one orientation, but then we went back in the other direction. So what's going to happen to those two pieces? They cancel out, because orientation matters. If you go backwards, you subtract, and so they cancel out. And so you can think of it as one big, long, continuous piece. That is one way to do it. There's another way to think about it, which is the following, and whichever way you prefer, go with it that way. So I can think about, here's my region, and if I integrate in this orientation, what's the contribution to the inside? Okay, well, this will make more sense in a second. Well, the answer is the orientation is consistent, so we'll call the contribution being as a plus right now. It's the plus orientation where I'm adding it in. If I have a piece here, and now I orient it in the opposite way, so in other words, I orient it clockwise, and I say, okay, what's happening to the contribution inside that curve? Well, if I have an orientation going clockwise, the wrong direction, what's going to happen? It's negative. So what you have is you have essentially like a plus part coming from the outside, and then a minus part coming from this curve. So this little piece got counted twice. This is one little overlapping part. One part had a positive contribution from the outside curve, a negative from the inside curve, and so the net result is they cancel each other out. And so it's like you have a hole. That's another way to think about it. Whichever way you like, go with that way. So let's do an example. Let C1 be the circle centered at the origin of radius 1, oriented clockwise. Okay, so radius 1, we're oriented clockwise, so we're oriented that way. So here is our curve C1. Let C2 be the circle centered at the origin of radius 2, oriented counterclockwise. So C2, circle radius 2, counterclockwise. So we're oriented that way. So there's C2. And let C be the union. So C is both these curves put together. It's perfectly fine to take unions of curves which are separate. And the question says, find the integral along this curve of this really long, terrible expression. And you're just like, this looks like a really long, terrible expression. That's kind of a clue. If you see something that looks bad, it says, don't actually do what we're asking you to do. Use the tools to do a better thing. So, let's not do this line integral as a line integral. Let's do Green's theorem. So what's happening here? Well, what's happening is when I look at this curve, which again consists of both C1 and C2, what do we see? There's a single region. This sort of flat donut, if you will. If you wanted to sound very fancy, you could call it an annulus. But it's essentially, our region consists of a big circle with a little circle punched out. So what we can do is we can apply Green's theorem and say, all right, let's do our Green's theorem. So we say, what's in front of our dx? Here's our m. In front of our dy, here's our n. So according to Green's theorem, this will be the integral over that region of, and we take n sub x minus m sub y. And we're going to do it dA. All right, so that's going to be the integral over our region. Now, let's come up to n sub x. What do we get? We get 1, right? Because that really terrible part goes away. Oh, that's good news for us. We like it when things get simpler. 1. Now we come up to m sub y. Well, what happens there? The e to the x to the 7th? Gone. The derivative of 3x squared y with respect to y? 3x squared. Derivative of y cubed with respect to y? 3y squared. Now, oh, you're right. That should be negative. We're going to subtract that. Got so excited. Okay, 1, subtract that. All right. How would we actually integrate this, though? Yeah, polar. Don't forget, you still have all these wonderful tools. So we like to start mixing and matching things. So be ready. Be ready. You probably weren't thinking polar. Well, maybe you thought polar because, like, I see circles. When I see circles, I think polar. So in polar, it's not so bad. What does the function become? One minus 3 r squared, because x squared plus y squared equals r squared. dA is r d theta. Theta goes 0 to 2 pi. And r goes from, well, coming here, we start at 1, and we go to 2. We always think about how we come out from the center. And we come out, and we start when we hit the first circle, stop at the second circle, 1 to 2. Now this is an integral which we can separate, so we have 0 to 2 pi d theta. Well, that's easy, that's 2 pi. And then we have integral of 1 to 2 of r minus 3r cubed dr. And so this would be 1/2 r squared minus 3/4 r to the 4th from 1 to 2, which is something. All right. Well, okay, we can be a little bit more precise. If you plug in r equals 2, you're going to get 2. And then you're going to subtract 12. And then from that, you subtract, plug in 1, you get 1/2 minus 3/4. And in the interest of time, we'll just leave our answer more or less like that. 2 pi times negative 10, because that's 2 minus 12. 1/2 minus 3/4 is minus the fourth, so this would be plus the fourth. All right. I know, so close. But good enough, good enough. We'll get the credit. All right. It is negative. Are we okay to get negative answers, by the way? Yeah, that's fine. No problem. No problem. Okay, so now, foreshadowing of some ideas, some important ideas. So suppose I have the following. I have t, which is the unit tangent vector, which means that if I have a curve C, so this is a curve C, and at any given point I have a unit tangent vector t. And I also have, over here, this is a force field. So these are the blue arrows. So these arrows pointing out. So I can now talk about what's happening on the boundary. So I can look and say, okay, let me do the following. Now for our vector t, we should note that t is dx, ds, dy, ds. We get that the integral along the curve of f dot t of ds is, okay, the integral along the curve of mn, that's our force function, dot t ds. Now, dot t is dx ds, dy ds. Well, that becomes the integral along the curve of m dx plus n dy. Okay, nothing too surprising. And then we have Green's theorem. So that's partial n partial x minus partial m partial y. Now, about a week ago, I said, we're going to reach a point, I'm going to say, that looks really familiar. We're at that point. That looks really familiar. And you're like, yeah, we've been using it all day, Steve. Of course it looks really familiar. But no. We've seen it before today. Partial n partial x minus partial m partial y. Where did that come from? Do you remember? It came from the curl. If you looked at the curl of MNP, partial n partial x minus partial n partial y was the third entry, the very last entry in the curl. And so we can say, okay, that's a piece of the curl. So in particular, it's the curl that you get of Mn, and it really can be anything here, so we'll just put 0. But we need to grab just the third entry because the curl is a vector. So what we'll do is we'll grab the third entry by doing a dot k. So dot k says, all right, just grab that third component. So if I want to integrate on the boundary of f dot t, that's the same as integrating in the region this curl mn0 dot k. Now, in terms of practical applications, we usually don't remember this way as Green's theorem, but we are going to go up into a higher dimensional setting. This will happen after the next exam, something to look forward to. And we're basically going to just tweak this ever so slightly and say, new idea. And we're like, whoa. But this is something that we're going to show actually works in a three-dimensional setting just as well. By the way, how do we think of k? Well, if I'm in the plane, the xy plane, where is k at in the xy plane? It's coming out of the plane. It's perpendicular to the plane. And essentially what k is telling you is, how do you stand on the plane? So coming up out of the plane, it's how you stand. All right, so here's what happens when we integrate this force dot our tangent vector. Well, is there something else we could use other than tangent? Okay, this is where I would normally give you a clue. The normal vector. Okay, all right. Someone cracked my secret code. All right. So we can use the normal vector. Now what's happening with the normal vector? Well, we want to talk about the perpendicular. So I want to be perpendicular to the curve. So I want to be coming out of the curve. Now, it's not so clear how to find the normal vector. So the tangent vector, that's actually not hard to figure out, because essentially we're saying, how do we change? Well, we look at x prime, y prime. That's what's going on with our tangent vector. Okay, that makes sense. How do you find the normal vector? The answer is, it's dy ds and negative dx ds. Now there's a couple things you can convince yourself of. First thing is, are these perpendicular? The answer is yes, because you take their dot product, you get dx ds times dy ds. Here you'd get the negative of that. So you put it all together, you get 0. So they are perpendicular to each other. That's a positive sign. This has length 1. This also has the same length, because you've just essentially swapped the order and changed the sign. So then the question is, okay, how do I know it points out and not points in? Because there are two ways to be perpendicular to the curve. I could point in one of two directions. So to help convince yourself, just sort of think of a point. So let's suppose I was way up here at the very top. And my curve, it's going from right to left. Well, what's true about the change in y? Well, I'm at the top, so it's 0. So that's good. What's true about how x is changing at this point? Is it a positive or negative as I'm going from right to left? It's negative. So if I look at negative of that change in x, it's a positive value, which means that I am pointing in the up direction. So it is consistent with being outward pointing. All right, well, now what do we have? Well, so the integral on the curve of f dot n. Well, that's going to be the integral on the curve mn dot dy ds, comma, negative dx ds. No big surprise. And if we integrate, if we multiply this out, we'll get m dy and minus n dx. Now, here's the tricky part. We got to do Green's theorem. But just be really careful. So Green's theorem says, take what's in front of the dy, take the derivative of that with respect to x. So we're going to get the derivative of m with respect to x. Subtract, take whatever in front of the dx, take the derivative of that with respect to dy. So what we're going to get is the derivative of m with respect to x, subtract the negative derivative of n with respect to y, which means that this is really a minus minus, makes this a plus. So we get partial m partial x plus partial n partial y. Now, I didn't prepare you for this question, but have we seen anything that looks like this before? Take the derivative of the first entry with respect to x, add the derivative of the second entry with respect to y. That's the divergence. So, when we integrate along the boundary of f dot t, that relates to curl. When we integrate along the boundary of f dot n, that relates to divergence. Now, why might we care about the integral along the boundary of f dot n? The answer is, it has to do with flow. So, if we say our vector field f, we're thinking that as flow. So maybe it's fluid flow, air flow, electrical flow. It's just flow of some sort. So these little arrows, things are moving. So something is moving. And I want to say, well, what's happening on the boundary? Well, to help understand what's happening at the boundary, you look at f dot n. That says at any given point how much is passing through your boundary. So f dot n times ds, how much is passing through your boundary at that point? Add it all up, that's your total amount going through the boundary. On the other hand, you can say, well, if I want to know how much is going through the boundary, I say, well, let's look at the interior and think about how much is either being created or how much is being absorbed. So in other words, you have sources or sinks. So what happens is you look at the divergence. Divergence asks the question, what's happening at your point? Are you a sink, you're having things come into you, or are you a source, you're creating things and you're pushing it out? So if I look at divergence of f dA, that says, okay, how much is happening locally? Then I add it all up. So I can either find the total flow by saying, let's look at the boundary, or let's look over the interior. So that's why we care about things such as the integral of f dot n. So what do we have here? So what we're saying is that the flow matches with divergence. And so this is actually a beautiful idea, and we're going to see this idea one more time. And I should point out, and I think it's good to point out, when you're doing a dot product like this, f dot n, what you're really doing is you're doing a projection. So what happens is, if I have something where the flow, let's say the flow is perpendicular to the surface, f dot n, and going out, then I get the whole amount of the flow. So it's just the size of f. But if it's, say, going in, then that says that the dot product will be negative. So it's the negative of the size of f, which means that I'm going out. And then, of course, if I'm perpendicular, the flow is perpendicular, well, then it's not going in or going out. And see the dot n, because if your n is here, that will be 0. So it does match with this idea. So positive number means there's an excess, more is going out. Negative number, more is coming in. So that's the way you should think about that. Now we need to do an example, and let's do one. So what do we have? Well, let C be the curve that starts at the point 2, 0. All right, let's do this. So we're at 2, 0, so we're there. Goes on the top half of the circle radius 2, starting at 0, 0, to negative 2, 0. So we go to there. So negative 2. Then goes on the, to negative 2, 0. Then goes on the top half of the circle radius 1, starting at negative 1, 0, to 0, 0. Okay, so there. So again, it's a big circle, then it's a small circle. And where are we at? And finally goes on the top half of the circle radius 1, starting at 1, 0 to 2, 0. So there. So there's our shape. We're going on the top half of a big circle, then the top half of 2 small circles. Now, find the flow across C for this vector valued function. All right, so if we're looking for flow, that says I want to integrate along my curve of f dot n ds. And one more thing, and I'm sorry, I'm going to interrupt myself, but I just want to point something out. This is flow through a boundary. You don't actually have to be a closed curve to talk about flow through a boundary. So I could imagine that I might have just a curve like this in space, or say in the plane, in our case, and I can definitely talk about, well, what's happening as I have flow passing through here? What's the flow? And I can add that up. So again, flow does not need to be a closed thing in order to talk about flow. In our applications, we will primarily use closed things to talk about flow. So we have that the integral around the curve of f dot n ds is equal to the integral, and that's our flow, over our region, the divergence of f dA. And now if you're wondering, wow, how do we know that? That's right there. Oh, yeah, that's a good reason. Okay, so let's take the divergence. So to take the divergence, we say come to the first term, take the derivative with respect to x. So what's that going to be? Well, y squared over 1 plus y squared. We got to integrate that? No, because we have even more coming up. Okay, now what? Now you go to your second term, and you take the derivative of that with respect to y. So plus sine of x cubed, because that's the derivative of this with respect to y, plus 1 over 1 plus y squared. All right, that's the divergence, dA. Now, we start this, we say, hey, good news. Those combine together in a nice way. And if you combine these together, what you end up with is you end up with y squared plus 1 over 1 plus y squared, which is 1. And we'll talk about that integral in a second. And then you have this other thing and you're like, oh man, that doesn't look fun. Sine of x cubed dA. All right, so one of these integrals is easy. And one of them actually is also easy if you think about it the right way. Now, let's start with this one that looks terrible. It does look terrible, and part of the reason it looks terrible is we can't integrate sine of x cubed. A good reason why it might be terrible. But let's think about what's true about sine of x cubed. It's a really unusual function, peculiar, weird, strange even, you might say. But among all things that might describe this is odd. What does that mean? Well, an odd function here says if I plug in a negative x, I get the same as if I plug in a positive x. That says in our shape, if I plug in sine of x cubed over there, and I compare it to sine of x cubed over there, they would have exactly different signs. But notice, this shape is symmetrical. So it means that the contribution from here will cancel out the contribution from there. And that's always going to be consistent. So when we look at the contribution from the left-hand side, that's going to cancel out the contribution from the right-hand side, which means that this part is 0 by symmetry. So that's cool. So we don't have to actually do that integral. What about this integral? Well, for that integral, we're integrating 1. Now, when you integrate 1, that finds what you're adding up. And what we're adding up is little pieces of area. And therefore, this is the area of our region. So, what is the area? Well, there's this big circle of radius 2, but we're only going to take the top half of it. So we're going to take 1/2 pi 2 squared, and then we've got to subtract off these little pieces. So half of a circle of radius 1, and another half of a circle of radius 1. So what do we get? Well, this first one, that'll be 2 pi, subtract a 1/2 pi, subtract a 1/2 pi. And if we put that all together, we end up with pi. And so that's the total. We get pi. Ah, nice. And notice that by using the theory, we were able to actually avoid doing complicated work. In some sense, you're going to see that's a theme of the type of problems that you'll encounter with this, is that you have things which look terrible, but then we apply a theorem, like this is essentially a version of Green's theorem, and then they suddenly look not so terrible, and we can handle them in simple ways, and sometimes we hardly do any integration at all. One of our favorite things, trying to avoid doing integration. Well, maybe that's not our favorite thing, but we're definitely not in calculus to do a lot of work. Our goal is let's do the right amount of work. So let's do one more problem. Let's see how much we can do without doing any integrals. Let C be the curve consisting of straight line segments between the following points. So we're going to start at 0, 0 to 2, 1 to 4, 0 to 5, 2 to 4, 4 to 2, 3 to 0, 4 to negative 1, 2 back to 0, 0. So it's a closed curve, and there's little arrows indicating how we move along those curves. Nice. Okay, so we can find the following. We find the integral on this closed curve, y squared plus cosine of x cubed minus xy dx, and 2xy plus 1 over 1 plus e to the 2y dy. Now the idea is, if I'm faced with a closed curve and I see the integral of m dx plus n dy, I say, all right, really that closed curve is bounding a region. And so I look at my region. And so this region, it's kind of a little bit of a strange shape, but it's a shape. All right, so here's our region, and we'll label this, let's call it R for region. All right, so applying Green's theorem, this is going to be the integral over our region of n sub x minus m sub y dA. So that means, recall, take the derivative of the second term with respect to x. And the good news is that did not look very fun to integrate, but because we're taking the derivative with respect to x, gone. Take the derivative of this with respect to x, and we're going to get 2y. All right, so there's n sub x minus. Now come here, take the derivative of this term with respect to y. Derivative of y squared is a 2y. And already we're like, ha 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 ha, look, it's going to cancel. Woo! Derivative of cosine of x cubed is 0 because we're taking the derivative with respect to y. Life is good. And, oh, wait, there's something left here. Derivative of this with respect to y will be a minus x. Huh. So this looks like we're going to have to find the integral over r of x dA. And now at this point you're probably thinking, wahaha, Steve has to do an integral, and he doesn't like doing integrals. But wait a second. Let's think about what we can do. See, here's the thing, is yes, this problem came from somewhere, but the question is, can we interpret this in some way? And the nice thing is, regardless of where your problem originally came from, you always have the freedom to interpret it in whatever way is convenient. And that ability to reinterpret what you're doing can sometimes give you a lot of power. So our question becomes, can we interpret this in an easier way? Now, one of the things that you might think of, saying, well, there's an x, and you can say, oh, one way to think of this is we can think of this as a moment with respect to the y-axis. Yes? Because that's how you find the moment, remember? And of what? Well, if our density was equal to 1. Because the moment with respect to the y-axis is x times your density dA. And now you're like, oh, okay, make density 1. Life is good. But how does that help us? Well, let's see if we can compute the moment. Well, right now, it's not so obvious how we might be able to compute the moment. But here's one thing to note. Suppose that our density was 1. Well, if our density was 1, our region here, it's nice and symmetric. And you see there's two types of symmetry. There's this symmetry here, and there's this symmetry here. Because in other words, you can fold it, or you can fold it. Which means that is the center of mass. So we get that x bar, y bar is at 2, 2. And what does that tell us? Well, this right here is the moment with respect to the y-axis, and we know that if we take the integral over r of x dA and divide it by the integral over r of just dA, because our density is 1, that would be our x bar. So we're able to use our interpretation and say, hey, because we have a symmetrical region, because we can think of this as a moment, and I can redo this as 2 integral over our region dA. Now, this doesn't always happen. You have to know how to interpret it. So don't think, oh, I can always pull this off. You have to have that ability and that freedom to interpret. And so I'm not trying to show this as like, oh, this is something which is an obvious tool that shows up all the time, but rather just to say, here's something you should always be thinking about and looking out for. This is something we would probably never do on a test, although this problem came from an old test. But not now. We're much nicer now. We're much nicer in front of your people. So, of course, now the integral of dA, what's that? Well, that's just the area. All right, so how much area is there? Well, if we look, we can really think of this as sort of a couple things. We have this little block here. There's 1, 2, 3, 4, 5, 6, 7, 8. And then we can break off these little triangles here. And now each triangle has base 2, height 1. So each triangle has area 1. There's 1, 2, 3, 4, 5, 6, 7, 8. What does that mean? Well, it means if you add the 8 triangles plus the 8 squares, the area of R is going to be 16, and therefore this integral is 32. And we're done. Good, good. All right. Well, Green's theorem is a beautiful tool, and so be on the lookout for it. How do you know when Green's theorem applies? Look for the integral of a curve which is closed. If you see an integral of a curve which is closed, that's an idea that says, oh, Green's theorem will work, especially if you see this really unpleasant-looking functions. When you see unpleasant-looking functions, it's not because your calculus instructor doesn't like you. It's because they're trying to send you a signal. Don't do that. That's a terrible thing to do. Be smart. Use Green's theorem. So, as they say, this problem was done by Green's theorem in the classroom with the fundamental theorem of calculus. Beautiful idea. That's it for now. We'll see you next time. Bye.